How's it going? It's Kyle, and I'm going to be starting homework 2 for computational methods, in which we want to numerically demonstrate the central limit theorem. So, real quick, the central limit theorem establishes that when independent random variables are summed, their sums actually tend towards a normal distribution, even if the original distributions are not normal. And basically we're going to prove that this is the case by creating data sets of random numbers. We're going to average the data sets, and then we'll plot them to see if the averages of those data sets follow a normal distribution. So let me get into it. So the first thing I did was we're going to be using numpy and subplots, so I just imported those real quick. And as I mentioned, we are going to want to have data sets, so we'll just say number of data sets. And the more data sets we have, the easier it'll be to see that it'll whether or not it follows a normal distribution. Because as with any statistics, it's a long-term view, so we'll just start with 1,000. I can always come back and change that. And then basically now I want to do the number of data points in each set. So this one is a little less important. Still want a lot, but I'll just start with 100. We'll see how that goes. And as I mentioned, we can use or we'll be randomly generating these data sets. So np.random, and we don't want to do it from a normal distribution because we want to show that even if our original distribution is not normal, the averages will still tend towards being normal. So we'll do a random uniform distribution from -10 to 10, and we'll do size of what we just named. So I want 1,000 data sets and 100 points in each set. Oh, I didn't run my imports. Alright, so there we go. And we can use numpy to also make a histogram out of this to kind of organize our data. So np.histogram, and in our histogram we want our data sets, all of our data, so we'll just call this we'll call this samples. And that way we can go up to here, do samples, and then we want to give it a number of bins, which is just how many groups it's going to sort the data into. So I'll just go with 20. And all of these variables I'm defining at the beginning, so I can go and adjust them if I want to. So now it's giving us our number of data in these bins. I did 20 since I had 20 numbers. It's pretty nice that it's -10 up to 10, essentially counting by 1. -10, -9, -8. And I'm going to store these as y and x because it'll be easier to plot. So looks like our first array is going to be the values I'm going to want for y. The second will be x, so we'll just call that. Then I can make a subplot, or make a plot. So make subplots. And then we'll add y to it. And we'll say x equals x and y equals y. So yeah, so if we take a look at this, we have our uniform data, and now what I want to do is I want to take the average of each data set, of all 100 data points in each data set, and then if I plot the averages, we should see that the central limit theorem says it should follow a normal distribution. So I'll close that and do a new line of code. So numpy has a mean function which will take averages for us. So if I take the average of my samples, and I want to take the average of each sample and put it in its own array. Take the average of each set of data and combine those into an array. So that means I have to give it an axis value of 1. If I just did the mean of the samples, it would take all the data and just take an average of it, which should be around 0 since it's uniform. So now I have the averages and I have that in an array. So I'll call this, we'll just call this samples 2. And now we want to make another we basically want to do what we did here again. So make another histogram. I'll call this one y1 and x1. And then we want to do samples 2, and we'll keep the same number of bins. Make subplots, and I want x to equal x1, y to equal y1. We'll run that. And as we can see, it follows a pretty normal distribution. There's a little bit of an outlier here, but like I said, statistics show a long-term view. So if I increase my number of data sets, it should much closer follow a normal distribution. So and same goes in reverse. So if I decrease my number of data sets, say I went with 100 data sets and 10 points in each set of data, I don't need this anymore. This is our uniform data. And we want to take a look at this. It obviously looks a lot less normal. But then if I come back and increase it, so we'll go 10,000 sets of data, and we can do 1,000 numbers in each set. And then take a look at this. This is very precisely following a normal distribution. So here we can see that the central limit theorem is true, and we kind of showed it numerically by taking a random sample of data and showing that the averages of all the data sets when plotted follow a normal distribution. So thank you.